Fairly, are you ready? Castle Park Gardens, number 2. Let's go!
It's time for Maths with Mr. Thomas.
Woohoo! We have made it to the end of complex numbers. This is the review lesson. Just like all the other review lessons, it doesn't include every slide and every example or much of an explanation. It's just me going over, very quickly, the key points. If you're wanting anything in more detail, look back to the individual lessons. This is just to make sure there is nothing that you have forgotten. So with this chapter, we started complex numbers with just an introduction to complex numbers, and we looked at what that is all about. If we go back to National 5 when we were solving our quadratic equation, we found that it couldn't be solved if we ended up with a negative under the square root, because you can't get the square root of a negative. However, that would mean there's no real solutions. But what we can do is we can find the non-real solutions by taking the square root of the negative. Negative 36 you can split up into 36 times negative 1. And if you have the square root of that, you get 6 root of 36 times the square root of negative 1. Square root of 36 is just 6, and the square root of negative 1, in maths we call it I. I for the word imaginary, it would be an imaginary number. So I is the square root of negative 1, which means you can continue with something like this, because you could write the square root of negative 36 as 6i. So you'd have 4 plus or minus the 6i over 2, and you can simplify that to become 2 plus or minus 3i. If you end up with something in the form real part and imaginary part, that is known as a complex number. A complex number has a real part, which would be x, and an imaginary part, which would be the y, so x plus yi. If you have something like 2 plus 5i, the real part is going to be the negative 2, it's a bit without any i's, and the imaginary part would be the 5, it's the coefficient of I. We went on to look at equal complex numbers, and complex numbers are equal only if the real part of one is equal to the real part of another, and the imaginary part of one is equal to the imaginary part of another. If you have that, then you can solve problems such as this one here. You've got a real part and an imaginary part, and it tells you it's equal to the real part and the imaginary part here. Because of that, you can equate the real parts to find out the missing values, and you could equate the imaginary parts again to get the missing values. We went on to look at adding and subtracting and multiplying complex numbers. So to add complex numbers, all you do is you add the real parts and add the imaginary parts. The same if you're subtracting, you have to subtract the real parts and subtract the imaginary parts. If you're multiplying them together, it's just going to be like multiplying out brackets. So multiply the brackets, 4 times the 1, the 4 times the negative 2i, the 3i times 1, and the 3i times negative 2i. But remember, because you would end up with negative 6i squared there, I squared is negative 1. Well done. So you can replace I squared with negative 1 and then go on. And it would be the same with this one. We then looked at what is known as complex conjugates. And the complex conjugate is denoted, instead of z, it would be z bar. And all you do is, if your complex number is x plus yi, the complex conjugate would be x take away yi. So you swap the sign of the imaginary part. So some examples here, you can see that the 2i would go to take away 2i. The take away 3i would go to plus 3i. The 4i here would go to take away 4i. And this one here was kind of a trick question because it's not a complex number. There's no real part and imaginary part. It's just a real number. So it would just stay as it is. With complex conjugates, you can go on and solve problems such as this one. Again, for a lot of the problems with complex numbers, you want to equate the real parts and imaginary parts if you're told that something equals something else. So the complex numbers over here equals this complex number here. Equate the real parts, equate the imaginary parts, and you can solve problems. The whole point in looking at complex conjugates is it allows us to divide complex numbers. So here if we've got 8 plus I over, or divided by, the 3 plus 2i, what you do is you multiply both the numerator and denominator by the complex conjugate of the denominator, as it says up here. So with this one, the complex conjugate of the denominator, swap the plus 2i with take away 2i, and it means you would multiply the numerator and denominator at the top and the bottom by 3 take away 2i. If you do that, you can multiply out the brackets. Once again, if you do that, you end up with an I squared term. I squared is -1. Good, so you can swap the I squared of a -1, that would be -2 times -1, so watch out for that. Once you work your way down, you end up with, again, a complex number, real part and an imaginary part. You can also look at square roots of complex numbers. This is something that we look at in one of the other lessons later on, but a very quick example here. You could work out the square root if you were given a problem like this. You could say the -21 take away 20i, you're wanting the root of that. Because of that, you know that you're going to have some complex number squared equals that. You can work your way through this problem and you can work out the values of a and b, and you can get the square roots. As I said, this was just a very basic example. There's more with square roots later on, as you can see up here with lesson 6. But after that, after the brief introduction, we then went on to look at polynomial equations. So a polynomial, you know, would be when you have like x cubed plus 2x squared plus 7x plus 3 equals something. So you can see here you've got your polynomial equation. We've got a z to the power of 4, 3, 2, 1, 0, and that's going to equal 0. We can verify that a complex number is a root by working out the value of z and z squared, z cubed, and z to the power of 4. So we'd work all of them out and then sub them into this equation. If we sub them in, what we should end up with is 0, because we're told that the left-hand side equals 0. So if we end up with that, then it means that that z equals the 1 plus 2i is going to be a root, which it is in this one. Write down another root of the equation. Well, your roots always come in conjugate pairs. So if the z equals 1 plus 2i is a root, the complex conjugate of that, z equals 1 take away 2i, will also be a root. So we can use that knowledge to then find all the roots of the equation. Because we have the roots z equals 1 plus 2i and z equals 1 take away 2i, what we need to do is we need to write them in factor form. So if they're roots, the factor would be the z take away that 1 plus 2i, and it would be z take away the 1 take away 2i. What we have to do is multiply these two factors together to get a quadratic factor, a larger factor. So that is what we're doing here. Once again, something you need to be able to do quickly is get the real parts and the imaginary parts together. So with the z take away 1 plus 2i, the real part would be the z take away 1, and the imaginary part, if you multiply out the brackets here, you'd have take away 2i, and that's the imaginary part. So get the real part and the imaginary part. Same with this one, get the real part, z take away 1, multiply the brackets, gives you plus 2i, that would be the imaginary part. Multiply them together and you would end up with that larger quadratic factor. We can then divide our original polynomial by that new quadratic factor. If we do that, we should end up with 0. We should get 0 because we know that we have this as a factor. And this remainder, or not the remainder, this answer up here, the z squared takeaway for z plus 5 would be another factor. So we can factorize that to be what we divided by, and then this part up here, this answer. And then the remaining roots will come from that z squared takeaway for z plus 5. And so, to work them out, you have to use the brilliant quadratic formula. Use a quadratic formula and you can get the other roots. That is a very long example, and I've gone over it very quickly. If you want to see it in more detail, look back to that lesson 2. Watch the video on that. Afterwards, we then went on to look at lesson 3, which was polar form. We started off polar form by saying complex numbers are made of two parts, a real part and an imaginary part. So we could plot them on a plane with an x-axis and a y-axis. But because it's a complex number, we plot them on a complex plane, which is known as an Argand diagram. And with your Argand diagram, you're wanting to show the real part, that would be the x-axis, and the imaginary part, which would be the y-axis. If we have the complex number z, which is x plus yi, we would plot the point P. The point, which would be x part is, the real part is x, and the imaginary part, the coefficient of I, is going to be y, so we'd be plotting x, y. That point would represent that complex number. In general, any complex number, z equals a plus bi, can be represented by a point. You're wanting to take the real part and the imaginary part. The modulus of z is known as really the length. It's the distance from the origin to that point that you plot. And the way you find it is just using Pythagoras. So you can say r is equal to, or the modulus of z is equal to the square root of the a squared plus b squared. And the a and the b you get from just this complex number when it's in the form of real part plus imaginary part. The argument of z is the angle that z makes, the line OZ makes with the positive direction of the x-axis. When you are working this out, what you'll have is your x and your y-axis, or the real and the imaginary, and the argument will go from 0 round to 180, and then from 0 round to negative 180. So really it goes between 180 and negative 180, or pi and negative pi, as it says here. What we can do is we could use some trigonometry to write our z equals the x plus yi, or a plus bi, in the form r, which is the modulus, bracket cos theta, theta is the argument, plus I sine theta. And that form there, r bracket cos theta plus I sine theta, is known as expressing a complex number in polar form. Why do we do it? Well, the whole point in that is it makes multiplying, dividing, and finding powers of complex numbers so much easier. Some examples with that though, from going from the complex form 2 plus 2i, for example, to polar form, what we do is we plot the real part and the imaginary part just as a coordinate. So here the real part's 2, imaginary part would be 2i. Forget the I and just have 2, 2. If you plot that, well, you need to work out the length from the origin up to here, that point that would be plotted, and that's known as the modulus. You find it using Pythagoras, so the modulus will be the square root of 2 squared and 2 squared. Work that out, simplify it, and you get 2 root 2. That's the modulus of z. The argument is the size of the angle it makes with the positive direction of the x-axis. So here it's just going to be theta. To get the size of that angle, use your basic trig. Tan is going to be the opposite over adjacent, be 2 over 2, which is 1, and then inverse tan, which will give you 45 degrees. Once you know the modulus and the argument, you can sub them into z equals r bracket cos theta plus I sine theta, replacing r with the modulus. In this example, it was 2 root 2, and replace theta with the argument. In this example, it was 45. There's quite a few examples with that, but I just wanted to highlight this one in this review lesson. We want to, for this, multiply the brackets first of all, and again plot the points. Because you've got this negative root 2 and then negative root 2, it means you're wanting to go back root 2 and then down root 2. So that point would represent that complex number. To work out the length of that line, the modulus is the same thing. It's just going to be Pythagoras. So r squared would equal the root 2 squared plus 2 squared. So r would be the square root of all that. In this example, works out to be 2. The argument though, just remember with the argument you're going from 0 round to 180 and then 0 round to negative 180. The best way to do this one, because it's going to be down here, is work out the size of this acute angle first of all. So we will just call that alpha rather than theta, because we're using that to work out what theta would be. Alpha in this case is going to work out to be 45 degrees, which means then that theta would be, well, we know around here would be negative 180, so then add that 45 degrees on. We know that the angle would be between 0 and negative 180, or really between negative 90 and negative 180, and we know down here it would be negative 135. So just check the argument that you get. After that, we went on to look at multiplication and division, which I just said is made easier using polar form. To multiply two complex numbers in polar form, all you do is you multiply the moduli together and you add the arguments. To divide, you divide the moduli and subtract the arguments. We looked at quite a few examples with that. With this one here, we've got the complex numbers z and w. We want to work out zw, so we multiply the moduli together. So 8 times the 2. 16. And with the arguments, we've got a cos 50, we've got a cos 30, so just add them together and we get cos 80. Same thing for sine, it's a sine 50, sine 30, add them together. To divide, well, when we're dividing, we divide the moduli and subtract the arguments. So we'd have the 8 divided by 2, which gives us 4, and if you subtract the arguments, the 50 take away 30 would give you 20. So we can work out the result of the division of complex numbers. After that, we went on to look at De Moivre's Theorem. So, De Moivre's Theorem, named after Abraham de Moivre, hello, that is used to work out the power of a complex number. If you're working out z squared, well, that's going to be z times z, and you end up with the modulus squared, and then you double the argument. If we had z cubed, we would cube the modulus and we multiply the argument by 3. If it's z to the power of 4, we would have the modulus to the power of 4 and we multiply the argument by 4. Really, what you do then is you take the modulus, whatever that is, and you have that to the power of whatever power of the complex number you want. And with the argument, you take, again, the power that you want and you multiply the argument by that. It also works for negative and fractional powers. So for example, with this one here, well, this is just what we were doing previously. We had to write z equal negative root 3 plus I in polar form. To do that once again, you would be plotting that point. You get the length of the modulus, the size of the argument. Once you've done that though, if you want to work out your z to the power of 4, well, what you would do is you would take the modulus, have that to the power of 4, so it's a 2 to the power of 4, which works out to be 16, and with the argument you multiply that by 4, so 150 times 4 would give you 600. That would be it in polar form, but for this example here, it's saying to write it in the form of x plus yi man. So what you have to do is you have to work out the cos of 600, it's negative a half, and the sine of 600 is negative root 3 over 2, multiply the brackets, and then you get the resulting complex number in the form x plus yi. Part C, we had to show that z to the power of 6 plus 64 equals 0. Well, that's just going to be the same thing that we're doing. Because it's to the power of 6, you've got the modulus to the power of 6, and we multiply the argument by 6. Work out the cos of 900, sine of 900, and again, you get it in that form with the real part and imaginary part. Here, there's no imaginary part, it's just the real part, negative 64. So if we add 64 onto that, we can show it equals 0. We then went on to look at the roots of complex numbers. That was something I had just in the first lesson, a very, very basic example, but this is looking at it in a lot more detail. There are two square roots of w, so in other words, two different complex numbers that when you square them, you get w. There's three cube roots of w, so three different complex numbers that when you cube them, you get w. There would be four fourth roots of w. So four different complex numbers that when you have them to the power of 4, you get w. Really, in general, for any positive integer n, there's n complex numbers that when you have z to the power of n, you would end up with w. So, with this example, if we're wanting to work out the square root, well, we know there's going to be two complex numbers that will give the square root. Whatever power we have is how many roots there will be, how many answers we will have. The first part here, I was just quite lazy, I didn't type it all up. I just said look back to this lesson with lesson 12.3 if you want to see how you write it in polar form. There's loads of examples in that lesson. With this lesson, it was really just looking at the roots. We have z squared equals negative 8 plus 8 root 3i, which means then, in polar form, that is what we would have. To work out the first root, well, because that is going to be the square root of z, we would square root this other side, and because we've got that to the power of a half, we would just have the 16 to the power of a half, which gives you 4, and we would half the argument, so half of 120 would give you 60. What we found was, if you look back to the lesson in more detail, you'll find that the roots are evenly spaced on your Argand diagram. So here, because there's two complex numbers, there's two roots, it's z to the power of 2, so two roots, they're evenly spaced. So if you take the 360 degrees and divide by 2, it means they will be 180 degrees apart. So all you do is you take the argument and add 180 degrees onto that, and then you can get 1 and 2 answers. You will get 2 roots. Showing them on the Argand diagram, well, because you've got the 4 in front, that is the modulus. So it means from the origin, you will be going out a distance of 4. From the origin, you're going out a distance of 4. Origin, distance of 4. What you'll find is when you go around that 60 degrees, really you're going around the circumference of the circle. So you'd be going around 60 degrees. With a 240, again, you're going around really 60, 90, 180, 240 degrees. Really here with your Argand diagram, even though you're really going between 180 and negative 180, that is still how it would look. Because if you take 360 degrees away from the 240, you'd get negative 120. And if you plot that, well, you'd still get the same thing. It would still look like that. Again, it's just going to be a distance of 4 away from this origin. If you end up with cube roots, well, the cube roots, there's going to be 3 of them. which means that you're going to have some complex numbers that when you cube them, you would end up with as 8i. The way you work it out is find out one of them. So to get one of them, again, you would have the cube root of z equals that complex number in polar form. Z would be that to the power of 1/3. You're wanting to cube root the 8, which gives you 2, and you would multiply the argument by that third. So you'd get 2 bracket cos30 plus I sin 30. Once again, because you know they're evenly spaced on your Argand diagram, you want to think there's 3 roots. So I'd divide 360 degrees, the number of degrees in a complete circle, divide that by 3, and the answers would be 120 degrees apart. So take your first answer and add 120 degrees onto it. That gives you the second root. For the third root, again, add 120 degrees. So you'll get the third. So you'll end up with the first, the second, and the third root. What we're asked to do in this example is to write them in the form x plus yi. So all you have to do after that is actually work out the cos of 30 and the sine of 30. Work them out and then multiply out your brackets, and you get it in the form of x plus yi. Do the same with this one, work out the cos of 150 and the sine 150. Same for this one, multiply out the brackets and you'll get your answers. Showing them again on your Argand diagram, you can see here that they are evenly spaced. There's the first one, there is the second, and here is the third, evenly spaced around the outside of this circle. After that, we went on to look at trig identities. With your trig identities, what they're doing is they're using a combination of the Moivres Theorem as well as Binomial Theorem to produce trig identities. So with this example here, we had to expand our cos theta plus I sin theta in brackets to the power of 3 using Binomial Theorem. So doing that, well, you know when you're using your Binomial Theorem, the general terms that you would get would be n r x to n minus r y to the r. Because this is to the power of 3, you know you're going to have your 3, 0, then 3, 1, then 3, 2, then 3, 3. You've got cos theta, so that goes from the power of 3 all the way down to 0. So you'd have the cos theta to the power of 3, then 2, then 1, then 0. So you don't need to write that. And with I sin theta, you'd have that to the power of 0, then 1, then 2, then 3. Work these out, remember, use Pascal's triangle to work out these binomial coefficients. So your Pascal's triangle, you start off with your triangle of 1, so you'd have 1, 1, 1. Add these two together to get 2, finish off with a 1. Next row, you're starting with a 1, add these two together, you get 3. Add these two together, you get 3, and finish again with a 1. So you can replace the 3, 0, 3, 1, 3, 2, 3, 3 with 1, 3, 3, 1. Work that out, and once again, as I said at the start of this review lesson, a lot of the time you have to collect the real parts. That's real because there's no I. There's an I there, so that's imaginary. This part here, there's no I, so that will also be a real part. So collect the real parts and then collect the imaginary parts as well. Also something to look out for. If you've got, for example, here you've got I squared. Remember, I squared is -1. Brilliant. So you can replace I squared with -1. If you've got I cubed, well, that's really I squared times I. I squared is -1 times that by I. Well, it's just -I. So look out for that. That is using our binomial theorem, but we also had to expand it using de Moivres theorem. So using de Moivres theorem, we know that because that's to the power of 3, we're going to have our modulus to the power of 3, but here really the modulus is 1, so if we have 1 to the power of 3, well, we don't really need to write that. What we would end up with is just a 1 in front of the brackets, but we don't need to do that. And with the argument, the angle, we'd multiply that by 3, so we'd have the 3 theta. So that is going to be expanding it using de Moivres theorem. Once again, you're wanting to compare the real parts and the imaginary parts. So the real part in this example is going to be the cos 3 theta. But what we did was when we expanded it using binomial theorem, we found that the real part was up here. So because we've expanded it 2 different ways, what we just do is we equate the real parts. And that gives us cos 3 theta equals this here. So it gives us the trig identity. With the imaginary parts, just take the coefficient of I, so sine 3 theta, and take the coefficient of I up here. So we can equate them as well. The sine 3 theta would equal this. After that, we looked at some more examples, again using de Moivres theorem and binomial theorem. But this one was slightly trickier because it also brought in solving an equation. So the first thing we had to do was just use binomial theorem. We did that okay. We're just expanding that using just the general term, expanding it, and again just taking the real parts and the imaginary parts. The real part here was cos 4 theta, so that's going to be equal to the real parts here, the bit without any i's. We did that. And the imaginary parts, take the coefficient of I, so sine 4 theta, and equate that to the imaginary parts here as well. We did that, but afterwards what we had to do was we had to show what tan 4 theta was equal to. And you had to remember that tan was equal to, well, that's equal to sine over cos. It is indeed so. Tan 4 theta would equal, well, that would equal sine 4 theta over cos 4 theta. Brilliant. Well done, Max. So, sine 4 theta, just take your previous answers. If you take them, sine 4 theta, you can see was that. So we'd have that, and then we're dividing it by with this cos 4 theta. This is what we ended up with, but we had to show it's equal to that fraction here, so we had to bring in tan. And the way we can do that is we could look at it and we could think, right, well, we know that sine over cos is equal to tan, so we have to think about what we're dividing by. Taking this part here, we've got sine theta to the power of 4. We'd have to divide that by a cos theta to the power of 4 as well. And because we're dividing by this cos theta to the power of 4, divide everything by cos theta to the power of 4. Doing that, well, because you're dividing the cos theta to the power of 4 by itself, that just gives you 1. We're dividing everything here. Just watch for the simplifying. And then from there, because you've got sine over cos, swap it with tan. Sine cubed over cos cubed, it's going to be tan cubed. Sine squared over cos squared, it's going to be tan squared, and so on. We then had to solve that equation. What we had to do was look back to our previous answers. This was a previous answer, and we just had to try rearranging that. And then a lot of the time, if you get a part C, it's going to link into that part A and B. And because we were able to rearrange the equation they gave us to have this equals 1, well, in our previous part B, we saw that that was equal to tan 4 theta. So we can swap that with tan 4 theta. So tan 4 theta would equal 1. With this, we were told theta was between 0 and pi over 2. So we're going to have theta between 0 and pi over 2. But in this example, we had 4 theta. So we had to think 4 theta would be between and multiply both of them by 4. So we're just wanting all the answers between 0 and 2 pi, or 360 degrees. Work out inverse of tan of 1, which is going to be pi over 4. And then you're thinking, well, tan is going to be in here, and it's going to be in here. These would be the two quadrants where it's positive. So it lets you get your two answers, and then just divide it by 4. Again, just look back to this lesson if you're wanting that in more detail. With this example here, again, just a slightly trickier example with the trig identities. We were given W, and we had to show that 1 over W was equal to the cos theta, take away I sine theta. 1 over W is just W to the power of -1. So we're working that out, and then using de Moivres Theorem, we've got this to the power of -1. So again, you'd have your modulus, the 1 to the power of -1, which would stay as it is, and we're multiplying theta by -1. Use the sine and cos graphs to work out what the cos of negative theta would be. Well, that's just cos theta. And work out what sine of negative theta would be. Well, that would be the negative of sine theta. We had to add the w to the power of k to w to the power of negative k, so that's just really using these two parts here that we are told, or the bit we're just worked out, and we'll get a formula for that. And then once we've done that, we just had to work out the w plus w to the -1 all to the power of 4. So again, it's using the binomial theorem, and it's using our previous answers with de Moivres theorem in order to get our identity. And we finished this chapter off looking at the locus in a complex plane. Remember, a locus is a set of points that share a property. You can see each of these little points here, they're the same in distance from a center point. If we had more points in, well, in order to be the same distance from that point, they would have to really fit around the circumference of a circle. Add more points, add more points. If a complex number moves in a complex plane, it will be subject to some constraints, such as the modulus is going to be something, or the size of the argument will be something. We'll be told what that is. And the path that z takes is known as the modulus of z. And we can find it. We can find the equation of that. What we need to do is we need to think about Working out the modulus is going to be the square root of the a squared plus b squared. That's how you get the modulus of a plus bi. We have to use that along with some other knowledge. A lot of the time it's going to be the equation of a circle. So the equation of a circle from higher. X minus a all squared plus y minus b all squared equals r squared. With this example here, we were told that the modulus of z is 3 and z is going to be a complex number. Because you know z is a complex number, you know it'll be of the form x plus yi. So we say z equals x plus yi and work out the modulus of that. It'll just be the square root of the x squared plus the y squared. Because we're told in this question the modulus of z is 3, we can say then that the square root of x squared plus y squared equals 3. Square both sides, we get x squared plus y squared equals 9. That's a circle equation! It is indeed, yes. So you can say then that locus of z will be the set of points that lie on the circumference of the circle with centre 0, 0 and a radius 3. With this one here, look out for the likes of this question. We were told that there's a condition where the modulus of z plus I is less than 2. And if it's less than 2, what it means, once you work through this, just have z equals the x plus yi, work out what z plus I would be equal, take the real parts and the imaginary parts, work out the modulus of that, so it'll be the square root of the real part squared plus the imaginary part squared, set it equal to 2, don't set it less than, just set it equal, and then you'll get an equation. We've got here the equation of a circle, but because we know it's going to be less than 2, it's going to lie inside the circle. If it was equal to 4, that would be it on the circumference, or if it was equal to 2, but because we know it's less than 2, it's going to lie inside. So look out for that. And the final example in this chapter, we were looking at what happens when we have, instead of the circle equation, maybe just a straight line. Here we're told the argument is equal to pi over 3, which means then that this angle is always going to be pi over 3, which means then we will have a straight line. That straight line is, no matter which point you take on that straight line, there's always going to be an angle of pi over 3 with your x-axis. Getting the equation, you're just wanting to use a bit of trig. You're coming along x, you're going up y, so we can call the opposite and the adjacent, the y and the x. Tan of the angle, tan of pi over 3 is going to be y over x. Rearrange that to get y equals. Just make sure as well that you think, right, if you extend that down, so you're going into the negatives with x, well, if you do that, the angle will no longer be 60 degrees. The angle is going to be negative something, which is not what you're wanting. Because down here, if you extend it, well, that there is going to be 60 degrees. But if you come back the way, you're going to end up with the negative. So down here, that would actually be negative 120 degrees because it's this angle that you would be measuring. So make sure you say then that x is always going to be bigger than 0, because when it's bigger, it's going to be the pi over 3. When it's negative, well, it's just going to be negative 120 degrees. So look out for that. That's it for the review lesson. That's a quick summary of all the key points, everything that you need to know from that chapter. If there's anything that you feel you're wanting explained in more detail, look back to the individual lessons, as I keep saying. Good luck, happy revising, enjoy, have fun, see ya, bye, toodaloo, woo, yeah.